first we'll cover diffusion and then basics of privacy. I'm assuming you all attend. You didn't attend, no? Did you attend privacy? Okay, fine. So first we'll cover diffusion, then very fundamentals of privacy, and then we'll go to what existing research is happening in privacy. Right? So okay. Yeah, roadmap for today. Let's start from diffusion models. So the problem is, if I give you some data set X, like n data sets, and now you need to learn the distribution of that data set. Like that data set would have some sort of probabilistic distribution. Like assume that these are numbers which are uniform, like 1, 2, 3, 4, and 5. So that distribution is a uniform distribution of size 5. Similarly, every data set would have some underlying distribution of it. So you need to learn that distribution first, and so that from that distribution then you can sample to generate new data sets which look kind of similar to your original data set. Make sense? So for numbers it's pretty easy. It can be a function or whatever. But then you shift to other modalities like say images and text. So I'm assuming you guys know what embeddings are, right? So there you convert them to, let's say, embeddings and then try to figure out the probability distribution in that. That's one way to look about it, but there are other methods which we'll right now see. So first thing is something called as, these are methods which have been applied, okay? So variation of kind of encoder. So what happens here is, you have image which, or any data set which lives in a higher dimensional space, you kind of compress it into a lower dimensional latent space. Like for example, take CNNs for example. You start with CNNs, convolutional networks. So you start with a bigger image and you kind of like compress it down to a smaller dimension, right? So kind of similarly, you map a larger dimensional space to a smaller dimensional space, and from there you pick a sample from the lower dimensional space and then map it back to the higher dimensional space. That's how you generate it. Fine. So the issue with this is you kind of lose a lot of fine-grained details when you're compressing the dimensions. Ideally, you would want a mapping between large dimensions to large dimensions, but that's kind of very computation expensive in this particular setup. So they can like put it into a lower dimensional space. So what happens is, then let's say you map an image to a number 1, and you map one more image, a similar image, to number 2. So then what you do is, let's say you take number 1.5 and then generate an image. So what it happens is, usually what they observed in this was, it kind of looked very blurry, like there was no sharp details in images because everything kind of looked like the mean of the nearest latent spaces where the original image was mapped towards. Like there was no sharp details in the image generated. So that's the issue with variation autoencoders. GANs, I think you guys were there when I told about GANs. Okay, like I said. So GANs is essentially, it's like a cat and mouse game where you have two components. One is an image generator and one is a discriminator. So generator is something which generates an image. Like let's say it generates a 256 cross 256 image. Fine. And the discriminator now has to, and discriminator is a classifier, just a normal binomial class, like two-class classifier, right? So it has to classify whether this image which has been given to it is either from the generator or is it a real image. Fine. So if the discriminator is guessing it correctly, that means the generator is not good enough to be not being able to be distinguished from a real image. So the generator improves its weights based on the probabilities given by the discriminator. Like if it's extremely good, like the discriminator is good, then generator improves. If the generator is good enough to like confuse your discriminator, that means you improve the discriminator. So it's like a min-max game. So the generator tries to maximize the probability of either the real coming from the real or the generator coming from the class coming from the generator. And generator's task is to do the opposite, try to confuse the discriminator. So there is no optimal solution for this kind of min-max functions, and it's extremely unstable to train again. if you have like cans are extremely outdated, like they were in use before diffusion models, but if you want to, you can try training a GANs from scratch, and it's extremely unstable due to this min-max loss which happens. Fine. And one slight like kind of not used very much is something called as flow models, where so right now what all we have been looked like, at least in variation autoencoders, what we look for, we map the the higher dimensional space to low dimensional space and load to higher again, and this all done by neural network, so they approximate the solution. But in normalizing flows, what happens is the function itself, like the mapping function, is exact and it's invertible. It's bidirectional. So you have f and f inverse, which is like not hardly defined, but it's an actual mathematical function. So again, the issue of this is because it needs to be invertible, there's not a lot of use cases which can be done. The advantage is you get extremely good quality images from this because it's invertible. You get the highest quality of images, but issue is it has to be invertible, which is not usually the case. Like you can't map high dimensional like images and text into something which gives an invertible function. Fine. So these are the issues, and now you have diffusion. Fine. So now instead of you like learning the entire process of like generating an image from scratch, these guys do it step by step. So again, how do we go about it? You start with an image. For now, let's until I explain diffusion, we'll take examples of images, then we'll go towards text models, right? So you start with an image. You have n by n pixels, fine? Now for each pixel, you add some noise. Now that noise is gonna be like mostly what it's used is a Gaussian noise of mean 0 and standard deviation 1. Right? So for each individual pixel, you add some noise, Gaussian noise. So one step, two steps, dot till some t number of iterations. Right? So the more number of noise you add, as you increase t, each pixel will resemble a Gaussian distribution. Make sense? Yeah. Constant, you keep on adding Gaussian noise, it becomes Gaussian. Yeah. Fine, we'll go into the maths soon, but yeah, this is the gist of it. So the forward process is well defined. You know the mean of the noise, you know
all
the
pixel values lie in a Gaussian distribution of mean zero variation.
Sorry?
All the pixel values basically lie on a Gaussian distribution of mean zero variance basically.
Yes, every individual value will lie on that. Okay. So this entire forward process is defined by you. Like you know what the mean is going to be, you know what the standard deviation is going to be. So let's say you want to reach some step n. You can directly jump to that step by doing math instead of like doing one simulation every single time. We'll come to that, but yeah, keep that in mind. So yeah, so forward at step t, we add a small Gaussian noise to t minus 1. Now this is the formula you have. So probability that given xt minus 1, what's the probability of xt? That is a normal distribution with mean of root 1 minus beta t xt minus 1, standard deviation of beta t. Fine. And when you open it up, it looks like this. So xt is under root 1 minus beta t xt minus 1 plus root beta t epsilon t, where epsilon t is a normal distribution of 0, 1. So essentially I'm just shifting the mean, like this is your mean, but instead of that I'm taking it apart and adding a normal distribution of 0 and 1. Like this is easier to work with. You get how we went from here to here. Understood? Fine. So essentially you are taking the last one, you are shrinking, you start with the pixel value of the last step, you reduce its impact and add some noise iteratively. So the original pixel values initial properties go down slowly and the noise properties go up. Right? And so beta t shrinks the signal and beta t is usually small. Like you do it like step by step. You just don't want a huge noise to be added immediately that you can't like unlearn the steps. The entire point of diffusion is you add noise slowly while like add step by step so that the back step is also kind of easy to learn. Right? So the signal shrinks and noise accumulates until xt itself is like not distinguishable from a normal distribution of 0, 1. Fine. This is the mean and this is your variance.
Beta t into
1. Like identity matrix. Like if it's an n-dimensional space, it's identity matrix. For now, let's assume 1 for ease of purpose, right? So this is the recursion, as you can see. Now you can obviously open up a recursion and get given x0, you can go to x directly, right? So that's what's going to happen. Yeah, so when you open up the recursion, this is what you end up getting. Xt is given by under root alpha t x0 plus 1 minus under root alpha t epsilon. And alpha t is your cumulative, essentially how much of the original is retained, how much of the noise is added. So again, when you open up this recursion, you start with x0 and you keep on substituting those values. This will keep on getting multiplied multiple times, right? And then you will end up with this. Fine. So this is a noising, like the forward step. So given your x0, you keep on adding noise and reduce the initial x0 values iteratively until you end up with pure noise. So now we have mapped your image to one probabilistic distribution. That is Gaussian noise of 0, 1. Now your job is to retrieve, like given like from any sample, if I take any value from the Gaussian noise, I need to get an image back. That's my end goal now. So now how we do is you iteratively run it back one by one. Now you may be asking, like, you know the forward step. You know step by step how the forward step goes. Why not just do it in reverse again? Does it make sense? Like for example, I have told you that the initial formula we started up was given xt minus 1, what's the probability of xt? Right? Now you know basically, then with given this, you can obviously find given xt, what's xt minus 1? Just invert it, right? Now the issue with that is, so that's what, so now what we do is, you need to train a network which can predict xt minus 1 given xt. Fine. Now a neural network obviously won't exactly find the reverse step, it will obviously approximate, so the approximation for now. You might be asking, why not just do this? Why not just directly compute this value? Which is fair to ask. Right? So when you expand it, so q of xt minus 1 given xt is integral of this. I'm assuming you know what this is. This case PDF. I'm assuming you know program for this. Have you done program course in STEAM? How do I explain this? Okay, for now, when I use the slides, I'll expand a bit. But for now, understand that to calculate this value, I need to know q of x0. That is the initial probability, the first image, the image itself. So to calculate the backward step, there's one particular step using Bayes' theorem, that is analytically, I need to know the initial image itself. And that is not possible during the image generation part because I want the image itself. Like if I knew the image already, why would I be doing this denoising and noising back? You get what I mean? So the issue right now is, if you want to calculate this step analytically, that is just by hard-coding math instead of a neural network, you need the original image itself, like how this, what this will end up to be. But we don't know that because that's what we want to find itself. So we use a neural network to approximate this so that without using the initial probability. So the
From the start.
so you have an image, you add noise, pure noise. Now one step back, one step back. This individual step is now going to be like that probability is going to be approximated by a neural network
Without using.
without analytically calculating anything. Fine. Okay.
But like, isn't it also possible for like linear form that xt is equal to root of 1 minus beta t xt minus 1?
Yeah.
If we find xt minus 1 in terms of beta t.
No, that's what I'm saying. To calculate xt minus 1 given xt, when you open it probabilistically, you need x of 0, q of x of 0. And that is the image being generated itself. Do you get what I mean?
That's some idea.
What?
Not fully, some.
Okay, see. So noising is done. You keep on denoising every single step until you reach the final image being generated. Fine. Now what I'm saying is, if you wanted to calculate each single step in pure math, just like how we define the initial noising step itself, I'm saying that to calculate that particular back step, you need x of 0 also in that formula. So you need the finally generated image to calculate that one particular back step, which is not possible because you're still in the denoising phase. If you knew that, why would you even be generating the image itself? Make sense? Fine. So you model the reverse step. So the noising step was a Gaussian noise addition. So you can kind of estimate that the denoising is also going to be some sort of Gaussian noise removal. Fine. So probability of t minus 1 given xt is going to be some value of mu. So last time we had it as root 1 minus beta t. This time it's going to be something which the network will learn. See, anywhere theta is given, that is parameterized. That is what the network is going to learn. And it's going to be some sigma which is going to be beta t from the last time. Fine. So the network is going to learn this particular mean value for each single step. Fine. So now to train mu, we need a loss function obviously. For any network, you need a loss function. You have classifiers, you need cross entropy, regression, and MSE. For this, you have elbow. Fine. So the objective is it generates some image. Fine. How do I put this? Okay, for now in easy terms for you guys, you can think of it as like it generates a probability distribution at x naught. So t minus 1, t minus 2, dot till 0. Fine. And there is going to be some probability distribution, that is one image being generated which is going to be the best result. That's the ideal case scenario. That is, when you train the model, you start with an image, you noise it, and when you denoise it back, you want the last image to be exactly the replica of your actual input image. Makes sense till now? Fine. So a reference is the input image itself. So you need to maximize the probability distribution of the output image with respect to the input image. Makes sense till now? Fine. But again, some math. You would have to like integrate over like you have essentially you have to integrate over every single step to find one of this, which is extremely tedious. Fine, you need something else to substitute for this because you need to calculate this. That itself is going to be extremely highly computation, and then you will have to like train your model, which is not possible. Like it's not efficient at all. So you need to have a substitute loss which kind of conveys the same message, but it's easier to calculate. Fine. So now what they do is something called as elbow. Fine. So this is log of p theta x naught. That is the distribution generated. Like assume this is the image generated by the model, final image. Fine. This is gonna be an log of integral of. At every single step, like what's the probability that it reached to that end image given the each denoising step. That is, you integrate all the probabilities across all time steps for now. Fine. Then you multiply two constants. Multiply and divide essentially. So this is given an initial image. This is the noising part. Q is noising and P is denoising. Right? Given an initial image, what's the probability that from time steps 1 to t, it took that particular path. Because noise again, like it's a Gaussian distribution, right? So if you sample a Gaussian noise, it's a random variable. So what's the probability that it took those particular steps from 1 to t? Make sense? So multiply and divide it by that. Now expectation is essentially, for now, assume it as mean. You know expectation, right? Fine. So expectation with respect to this, like you, whatever, fine. For now, assume that you take values from here, and this is the expectation for now. Keep that in mind, okay? And then, do you know what Jensen inequality is?
What?
Jensen's equality.
So,
Okay, do you know what a concave function is?
like gradient function.
Okay, no. So how does a log function look like? It looks like this. It never changes slope. Like it's always like a bowl shaped up downwards facing. Makes sense? So convex is upwards facing and concave is always downwards facing. So a mathematical definition of this is f of double derivative of function is always less than 0. That is a concave function. Yes.
Yeah.
Make sense? So there is an inequality which holds for a concave function. As you might follow. Fine. So when you apply this, you get, so you have inside log you have this. This is your y. Fine. Log of expectation of y is greater than expectation of log of y. So you put it over here, and this is your, what do you call it? Loss function. So essentially, you are shifting from p theta to this. We established that finding this is difficult, and I'm going to show that finding this is slightly more easier. So you have an upper bound. So if you minimize, like this is bounded by this. So if you minimize this, in some sense, you're minimizing this also. Fine.
What is that expectation thing?
Okay. Expectation in mathematical terms, I don't have to talk about.
You can draw it.
There. Oh yeah, I can draw this. Can I draw now? Oh, I can. So expectation of x is given as integral x p of x dx, where your x is sampled from dx itself. So you sample every point of x from the probability distribution p of x. This is the form. Like this is like mean, essentially. Expectation is like the mean of your probability distribution. For example, you take, or let's assume p of x is defined as what do you call it? 1, 2, 3, 4. I don't know. This occurs one time. So it's gonna be, oh wait, there's some bullshit. Okay, this is just stupidly defined.
We can take Gaussian as
Yeah, so if you take Gaussian itself, then your p of x is the Gaussian.
P of x equal to x.
No, I made some stupid mistake. For now, assume p of x is Gaussian. Fine. So for find the expectation of a Gaussian, what you do is you do x 1 by root 2 pi sigma square e to the power minus x minus mu whole square by 2 sigma square from some range to some other range. That's how it works out. Fine. How do I raise this? Can I say what? Okay, fine. I think so. Fine. Expectation is like, for now, assume it's the average. Like in easy terms, it's the average of a particular function in a given range. Fine. So,
weighted
hmm?
average, because x.
I won't say weight.
Everything is equal.
Hmm?
It's like mean.
It is kind of mean. Like I don't want to say it's exactly mean, but for now, like for ease of understanding this, assume it as average of that.
What is the center of the curve? Like,
What do you mean center of curve? It's like in Gaussian, yeah, you can say that. Like if you have seen a Gaussian curve, it's like what? You have to wait for this to pop up. Yeah. So if you see the Gaussian like this, in Gaussian, this is the mean. Right. So yeah. Okay. So as I told, this is given an input image. What's the probability that it traveled through a particular path of noising? Fine. So how do you find it? Like it went. Like what's the probability that it went from 0 to t in these paths? So for it to multiply the probability of each single noising step. Make sense? So if you open this up, it becomes probability of 1 given 0, probability of 2 given 1, 3 given 2, dot, 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 dot. So you multiply all of it together, you get this. Fine? Just the opposite. Fine? What's the neural network is going to learn the flip side of it. Fine? Good. So now as this was our objective to find, you substitute these over here and you get this equation. Fine? Make sense? So now we apply Bayes' rule. This given xt minus 1 is this. So what's the probability of t given t minus 1? So see, because this is how do you put it? So this is something called as Markov chain. This entire process where the immediate next step, that is q of t, is only dependent on t minus 1.
So x1, x2 also.
So x2 will only depend on x1, and x3 will obviously always depend on x2.
Over there, instead of x0, if we had x of t minus 2 also,
it won't make a difference. Fine. So Markov chain essentially, like as I mentioned over here, like this is just for mathematical accuracy, but Markov chain essentially means a process where the next step only depends on the current step. Like in mathematical terms, it doesn't depend on the previous step. Fine. So you have this. So if you put anything else over here, it doesn't matter. Fine. Because xt will obviously only depend on xt minus 1. Fine. So you do some jargon math. I'll leave this for now. I'll just show what the end term looks like. Fine. You can refer this back and I'll leave the slides later. Fine. Because like this is not my major objective of today. We'll just skip through the math a little bit quickly. So at the end you get this function. Now I'll take some terms down for you. So dk, this particular term, again all fancy notations, it's like the math itself is very like. So this is something called as scale divergence, which is calculated between two probability distributions. It is given as p log of p times r. Yeah. So what this signifies is, I don't want to mess it up just a second. It's closer far. Let me check.
P side should be symmetric.
Wait.
P and q.
What?
P side it should be symmetric above P and q.
Yeah, just a second. Yeah, how, if you calculate this, how different is q from p? Like assume p is equal to q, you get 0. Fine. So this essentially shows, given a function like probability distribution p, how far is q from p itself. Fine. And also notice p of q is not equal to q of p.
Yeah.
Q of p becomes q of log of q by p. Fine, okay. So that's what you do, like you can just substitute the value over here. So like if you want to expand this, you need to just put P as this function and Q as this function. Make sense? Alright. So your loss essentially comes down to this is called as reconstruction loss, where this particular component where you kind of measure given x1 how close it to x, how like what is x0, like the last step of denoising essentially. Does it make sense? Like we'll come back to it. And this is what's the probability of xt, like the last stage of noising given x0 with respect to p of xt. Now p of xt is the final noise which you define, that is the normal of 0, 1. So if t is sufficiently large enough, these both will just be the same. Does it make sense? If I start with an image and go to a very large t by adding consecutive noise with normal 0, 1, which is this, it becomes normal 0, 1. So this essentially kind of becomes 0 itself, because we saw that k divergence is 0 for to equaling whatever. What? Sit. Fine. Okay. Fine. And this, for now, understand that this is like comparing. So this, as we showed, we could calculate it analytically, like over here. This can be done by pure math. Any term involving Q can be done by pure math. So given xt and x0, you can calculate t minus 1. Yeah. So you can calculate the noising steps, like t minus 1 to t noising. So given that final noise addition, what's the probability of the previous step? That can be done by base theorem, right? We are comparing that with the prediction of the neural network itself. So given t, what is it weight for t minus 1? And then you check the k divergence of it. So if it is less, it's good for us because both of them are matching. And as we established, like this is the reference, like in p given q, it measures how close is q towards e, means in that equation, but here we measure how close is this to this particular distribution.
So is inside the e. Moving is inside the e function.
Yeah, you do it for every single time step. Fine. And if you look at it, this is kind of same to this. Like here it starts on t is equal to 2. If you put t is equal to 1, you will get this. Because there's log terms, if you put t is equal to 1, I think it causes some sort of instability, so they kind of remove it and put it over here. Fine. So this is your loss which you need to minimize for your diffusion model. Clear? So to recap quickly, you add noise, you get some, this is the training phase by the way, not inferencing. So you start from an image, keep on adding noise, fully convert it to noise, denoise it, and at each single denoising step, you measure the noising step for reference and see if it matches and do it for every single time step. And that's your loss essentially. Works? Cool, okay. So I will come back to this at the end. I don't want to like go there right now. So now coming to LLMs. Like for this was completely images. Like this was all continuous. Like at no point of time was anything discrete over there. Noise addition and everything was this continuous noise. Like it was only Gaussian 0, 1. But in text you can't do that. Why is it? So think of it in this term. So in LLMs, what happens to text in the first stage? What do you do? You tokenize it. So essentially convert a text word into a string of numbers. Now if you add noise to a string of numbers, what happens? Exactly. It just removes the entire context of it. You don't get anything out of it. Right? So a standard method of adding a little bit of noise won't work over here, because it essentially just destroying the meaning of the word itself, like how language itself is built from scratch, right? So that's one thing. So we move from continuous noise to discrete noise, right? So quick recap for LLMs. what you do is, given a string of tokens, what's the probability of the next token? That's all you predict, right? That is autoregressive. And I'm assuming you have guys have attention maps. Attention. Some idea we have. Okay. So for now, what you need to understand for attention is to generate the next token, it refers to the previous words. Now that is called as causal. It only has access to what has been generated till now, not in the future. So like once a token is generated, it stays fixed. Now that like you have t minus 1 tokens, the tth token is generated. For t plus 1 token, t tokens will be its reference for creating attention to figure out what word to like give focus towards, right? And generation is only left right. Once it's committed, it's done. It doesn't change later onwards. Like when you see an LLM, it will obviously generate token by token, but once the token is ready, it won't go back. Works? So now what happens is, I'll just go to this. Yeah, okay. So here, instead of destroying a pixel or something by adding noise, what you do is, in the training process, you have string of tokens. Let's say you have some string of tokens which you train. Fine. So what happens here is, step number 1, you have to add noise. You need to destroy this into something pure noise. But we have established we can't add numerical noise. So now what you do is, in every LLM, you create a new token that you symbolize as something called as mask. Now this mask will act as your noise. So you convert an entire token into the mask token. Fine. For example, assume this at t is equal to 0. Now at t is equal to 1, randomly you just convert this particular token into the mask token. Okay. Fine. Secondly, you do this. Third, you convert this. Fourth, you convert this, and fifth, you convert that. Make sense?
How is different than what is the decoding of transforms? Attention.
We'll come down. This is for now. It's still under adding noise.
Okay.
Fine. So how it's done is, at every time step, with some probability, let's say 1 minus p, it will stay as the token itself, and with probability p, it converts into the mask token.
What exactly is mask token?
So see, essentially, you have some vocabulary of English words. You have some 60,000 words. Each of them has some token attached to it, right? Now I'm defining a new token which acts as noise for me, which doesn't mean anything.
Gibberish.
It's kind of gibberish. For the computer, this means it's gibberish. Like that also will have some sort of embedding. Like the mask token will also have an n-dimensional token, like with all some numbers and all. But what happens is, you substitute this word's embedding with that word embedding, and do that for every single thing. Right? So again, as I told, so with probability, let's say 1 minus
like similar to replacing suppose there's a word like river, you replace it with something like R, D, S, K, like that kind of thing.
What is
Like
that?
suppose like there's a word like I have river.
Yeah.
I replace that as like certain embedding so the vector side like that thing is there.
Yeah.
So instead of writing, suppose so now you're saying there will be another vector which has some numbers are there, which doesn't have any meaning to us.
Yeah.
So if we try to convert that to text, either the computer will fail or we get some random answer. That's the only.
No, I still don't quite get you.
See, suppose I have a word in that sentence I have a word river.
Okay.
That river is there.
Yeah.
It has a certain embedding, the
Yeah.
number I have certain numbers. Okay. Now you're saying that instead of these set of numbers, I
Yeah.
will put another set of numbers which are random.
One set of, just like mask is going to be just one number.
Okay, one number in that whole set will change.
No. See, okay, let's put it this way. So, see, every token, every word has numbers, like embeddings. Let's say n cross one dimension. Fine. Now, mask also will have some n cross one. It's like I'm assigning this new embedding to be something to be, I'm telling the model to look at it as noise. Now when you decode it, it will try to convert a mask token into a normal word token. It's just, see, if your vocabulary has n English words, like a probability again, as I told you, autoregressive models work like generating probability distribution given xt minus 1 tokens, right? Now the vocabulary will have some, let's say, m components. It will give probability distribution for all the m, pick the top one and substitute and then go forward. I am saying just increase the vocabulary by 1, add that for like map it to the mask token. Fine. And now with some probability, like at every time step, with some probability p, let the initial token be the token itself. Or with 1 minus that probability, replace it with the mask token. Essentially, instead of adding one singular noise, just completely converting the token into something else. But again, not numerical noise, something which the LLM can understand. So we are keeping it as an embedding itself. Makes sense, or not? Yeah.
Are you trying to do it for words, or does it make sense to try to add noise to words?
I'm not adding noise to any word.
What are you trying to do?
See, the point of diffusion LLM is you generate, let's say, a string of 50 mask tokens and then iteratively remove the mask tokens with words that make sense. And it need not be in order. It can be from in any single place. So it has bidirectional full context of all the words at every single point of time. That's the objective of a diffusion LLM. That's how it differs from an autoregressive model. You get what I mean? So instead of an autoregressive model like generating token at a time, it starts with all masks. Let's say M, whatever.
So, like, we give it the number of words we wanted to answer it, and then it will.
Essentially, what happens is like the models itself will have like a length inbuilt in them, and that's sometimes like big enough for you to like not have them define it yourself, but it is inbuilt. So what happens is you have these mask tokens. First, it will, let's say, convert this into a word, random word. Fine. Now it has again the context of all of these words, masks and this token, and given this token, it may then try to like denoise this mask into some word.
Chosen at random.
So initially it's random. The first couple of steps where it doesn't have any context at all, it's going to be random. But as more and more words come into place, like let's say Harry Potter. Harry Potter goes to Hogwarts. Let's say Harry and Potter were denoised first. Then it makes a lot of sense for Hogwarts to be denoised next because that gives attention to that. So I'll come to it, but for now that's the gist of a diffusion LLM. You have mask tokens, you iteratively add mask tokens based on some probability and try to remove them back to generate the text itself. Yeah.
Would you have problems with different types of tokenization?
Okay.
Because you are, let's say, you're denoising after Harry Potter, you're denoising the 5th token next day.
Yeah.
But it could have been 2 word and it could have been, or it could have been 2. And then if you use something like byte and encoding, there are different tokens. They're different in vocabulary.
What do you mean different vocabulary?
Because 2 words has occurred n number of times,
Okay.
you got 2 words as a separate token, right? Like in your vocabulary, 2 words is let's say another token
Okay.
and 2 is a separate token.
Okay.
Now when you denoise, how would the model know what to put where?
It has the forward denoising also in context.
Yeah, but like the length also matters, no? Like if I'm putting something, see, if I'm predictably.
Also, it's iterative in the sense like once a token is generated, it's not fixed.
Okay, it can change in the next step.
Yeah, at every single time step, it has context of everything.
And after a point that settles to something in the latent space and that you decode to a token, is it?
Meaning?
Like if it's iterated, it just settles somewhere, right?
Yeah.
Everything is denoised.
So yeah, your final loss is again going to be compared to the initial sentence, no?
That's when training.
That's what it
Inference-
is. You learn the thing.
No, like my question is, if it's iterative, then does it settle at a point like after everything has been sufficiently?
Yeah. There's no like n number of timestamps. After a point, then everything will just be the same probability distribution. No? Like once your sentence is formed, which is coherent, then each token will again point to the same token.
Yeah, got
So it makes sense. And one more thing, for generating the probability of each of these words, you still use a transformer beneath the model. Do you know what I mean? Okay, so as I mentioned, you have vocabulary B with dimension M, and you add one as mass token.
Yeah.
So now so the training part is this, but for predicting each token, like what word should come there, still a transform model is used. Like given these tokens, like M, some random word, what's the probability that a certain word would come in this place? So to generate the word token itself, a transformer is used beneath the diffusion model. But how it's generated, what attention is given to it is different from an autoregressive LLM. So the transformer model has attention towards all the words at all points of time. But in an LLM, it only has attention towards the first couple of models, first couple of tokens while it's getting generated. Make sense? Clear till now? So the process is, you take mass token, each token keep with probability 1 minus t, mask with probability t. Fine. And finally, all tokens are masked, fully noised. In the reverse, predict the original token. For each token t, what was the initial token? Fine. And cross entropy laws on mass positions. Fine. Okay, so how this is done is, this is something called as, so in the initial diffusion, we had the equation of q of t given t minus 1 was adding like 1 minus under root of 1 minus beta t xt plus beta t of the noise, right? Here what you have is, let's break this down. So you have a matrix which is, so you have the vocabulary, you have the properties of the vocabulary. So what this means is, with probability 1 minus beta t, the initial token will stay in the token form itself, like the word will remain as the word. Fine? Make sense? But with beta t, it goes to mask. Fine? Okay, wait, I'll just open this up. So 1 minus beta t times identity. That is this. Fine? Plus beta t, okay. You add beta t at the last couple of rows. So what this essentially tries to convey is, once a token converts to the mask token, it doesn't go back to the text token. And a vocabulary word would only be in its own state. It doesn't go to a different word. Make sense? So, for now, I was like map it as this, word to word. So word to word is going to be 1 minus beta t. Word to mask is going to be beta t. But mask to mask is always going to be a probability 1. Make sense? So this is mask to mask. That's always going to be 1. And mask to every other word is going to be 0. Clear? So at every step you apply this transition matrix to all the vocabularies in the sentence. So every word remains at its own with probability 1 minus beta t, mask to beta t, and once it's masked, it doesn't go back to the word itself. So that we preserve the mask token as it is. Like once you add noise, it remains as noise. Clear? Fine. So yes. So your sample sequence, you add noise, you mask the token with probability t to produce xt, and then you pass it through a bidirectional transformer which has context on both sides. One of a good example is something called as BERT. If you have heard about BERT, BERT is something which has bidirectional attention masks. Fine. I've seen the 3 blue, brown, 1 brown attention video. In that, he removes the attention values of the bottom triangular matrix because you make it causal, like you don't give it context to the next couple of tokens. But here you give it. Like the transformer at every single point knows the entire attention span across all the tokens at every single point of time. Fine? Yeah. So transformer sees the full partially masked sequence leveraging both left and right context simultaneously. Fine? Okay, so yeah, so finally GPT is left to right, one token at a time, and single forward pass per token. Right? Diffusion LLMs bidirectional context. All tokens per step. Every token has equal probability to get denounced at every single point of time. Right? And multiple forward passes, like iterative steps to denoise it completely. Right? So this was diffusion LLMs. I just wanted to cover the basics. So quickly recapping: diffusion, add noise, full noise, remove noise step by step using a neural network. The math of it I skipped for now. It's there in the slides. If you have time, go through it. I left it because you guys are not done probab yet. Like I didn't know that. So fine. So privacy, quickly I'll just again run through the foundation. So the issue is LLMs. For now, I'll give it back to auto-regressive LLMs, fine? Normal GPT models. The issue is they memorize at some level, fine? Like for example, if you ask it, like at least earlier models, if you had asked them Harry Potter, like if you had given them like say 2 sentences of Harry Potter, it will like spit out the entire sequence of the actual book words like verbatim. So that means a particular source material you identified that was used in the training. Because if it had not seen the Harry Potter book, there is no way that it produced those tokens randomly in that particular sense. The probability of that is just extremely low, impossible to be honest, right? So this kind of is like fine in, let's say, a normal world GPT models, right? For example, if you ask it, what's the capital of India? It says Delhi. Now that's not a privacy leakage. Fine, it's just openly available information. And these textual books which are trained, let's say Harry Potter books, like the issue might be that those books are copyrighted. So if the, let's say OpenAI or Anthropic doesn't take proper copyrighted, request from the author itself, then it's a violation of the copyright rules, right? So there have been cases like that also where these frontier labs have been accused of like training on copyrighted materials, like by pirating or something, right? That is fine, but the issue then becomes what happens is, let's say you train on sensitive data like medical imaging data, right? And then you release the model publicly. And if you now query something and it releases the information about what it was trained on, like the patient name or something, their titles, which is like a gross violation of privacy, right? It needs to give a general idea of, like, based on the data, it needs to give some information to you which it has generalized over all the data set. Like if on X-ray scans, if these fractures on the shoulder look like this, that means you have to give this medication. But then if you prompt it saying, okay, this patient, what kind of fracture he had, and if it replies it, that means the model is like violating like health concerns, right? So this is the like one of the ways where you formalize privacy. So a randomized mechanism M is like assume for now your algorithm, like your neural network, right? Your model is epsilon delta differentially private for all neighboring data sets D and D cross. That is, you take 2 data sets D, fine, and the D prime is gonna just differ from D by 1 entry. Like for example, you have vector of n. So D and D prime will be both of length n, which will only change at one index of, let's say, I. Rest all is going to be just the same. Fine. And now you put that into your model and you check for the output. For now, assume this as probability that giving input of this in data set into your model outputs something. Fine. Let's say this can be a class, like in multi-class, whatever. Fine. Is less than or equal to e to the power of epsilon probability of the adjacent data set giving the same output plus delta. Fine. So how this looks is in a kind of an easy way to put. Let's say for a given data set, the probability or like the distribution of the output of the algorithm for D looks like this, and for D prime looks like this. Fine. Now this is your epsilon. Fine. So what here it means is just by the difference of one particular data point in the data set, how much of the output distribution splits apart. Make sense? So if it's very large, then obviously you can for sure tell that that particular number which was swapped was maybe used in this data. Let's say for example this loss distribution, right? Let's say D prime moves extremely like large. That means that particular data point was used in training. Makes sense? Fine. So epsilon is like the distance between the distribution of two outputs of your model. And delta is, for now, take it as, what's the probability that this bond doesn't hold? That is at some, like, what's the probability it fails at some point of time? Fine. In usual, like, in math, how do I put it? Fine. So smaller epsilon, that means if it's very close to each other, that you can't distinguish these two both, that means it's stronger privacy. And if you can't distinguish, that means it's weak privacy. That means you can distinguish which model gave what. Fine. So how privacy is framed is, So defender is the one who prepares the model, trains the model on private data D. Fine. Releases the dates like open source. Fine. Now the attacker will query the model with some target. Now let's say for example image classifier. Let's say someone trained it on image like CIFAR 10 data set. Some CNN model they trained and they release it towards the world. They don't tell what was it trained on, like what data set it was trained on, but they only tell, okay, I trained image classifier models on 10 animals, here's the data for it. Now you are like, okay, you have a doubt that maybe they trained it on ImageNet. So you take the model, you pass the image of ImageNet on it, calculate the loss of it. Let's say cat. From ImageNet, you calculate the loss. Now then you take another picture of cats, a normal picture which you took, and calculate the loss. Now, which loss will be higher? Sorry?
How do you calculate the loss?
The last probability distribution, like, okay, so let's say it's multi-class, like 10 classes. Every class will have some probability. Different ways, which have the higher probability. Which one?
Loss of picture, right?
Is going to be higher because the model hasn't seen it. Now, if you do this experiment for multiple images from ImageNet and your image, then you now have conclusive evidence that okay, ImageNet was used in the training with some probability. Fine. So that's what the attacker does. Now, if you can't distinguish it, that means it can't conclusively claim that some data point was used in the data set. Make sense? So membership influence attacks empirically test the defender's privacy claim, like how private is your model. Fine. So what metrics usually they use is something called as FPR, and like how many times can you successfully correctly claim that a particular data point was used in the training. Do you get it? Like let's say you have a model. Okay. Let's say you have an LLM and you fine tune it on some 1000 data points. Fine. And now you have 1000 more data points which were not fine tuned. So now you have a total of 2000 data points. Yeah, so you have an LLM and you have 2000 let's say data points. Fine. 1000 of which I am using it to fine tune my LLM model. That means now this LLM has been trained on further 1000 of these data points. But 1000 of them are still it has never seen before. Fine. Now you apply some methods which are called membership inference attacks. That means to figure out how private data like a model is. What you do is you get the LLM now, and with your method, you let's say shuffle like bring these 2000 data points again. You feed them one by one, and based on the method, you see how like whether it can classify correctly that this was used in training or this was not used in training. Make sense? If it calculates it wrongly, that is your false rate. So you kind of do metrics at 0.1% false positive rate. That is like at that amount of FPR, how many times it can correctly classify your actual in-use training number. Fine. So now we move to existing stuff what people have done. So the initial, like the most basic thing what people do is something called as training shadow models. In the sense, okay. So you have a model which you have to test your privacy on. Right? Let's call it f theta, and you have a target sample x. That is, which you have to test whether this data point was used or not. Fine. And now you have a couple of shadow models. Shadow models mean which you are going to train separately. Fine. So for every single shadow model, what you do is you train the shadow model on a data set, including x, that is your target sample, and you train one more shadow model on data set excluding x. Fine. And you record the loss of when you then run the inference on your models. You take this one and you record the losses like this. Fine. So then you get the ratio. That is then wait. Yeah, essentially what you're doing is you're calculating the ratio between the loss given by the model including x and excluding x, and you take this and you see how, and then you calculate the loss with this also. Then you see if it looks closer, if if it was trained, then the loss of this and that should be similar. Like if f of theta was trained with x and your shadow models which you trained with the sample x, their logic losses look similar, that means you can say with some amount of clarity that x was used in training. But if it looks similar to not excluding x, that means you can say it was not used. Fine. So this is the most shadow models essentially is like, let's say someone releases an image classifier model, but they don't tell what actual dataset they used. So but you can kind of guess what they use. So you try to build a data which is kind of similar. Let's say they release some medical dataset on knee injury. So you take some publicly available knee injury dataset, which is not exactly same but kind of captures the vibe. So that the model kind of understands what the task is, then you can then add your sample and then test it on that. Fine. So second is, wait, I'll just neighborhood. This is the neighborhood comparison one. So what this does is, let's say you have a string of tokens, text tokens. Fine. 1 till e. Okay. So you have some n number of tokens, fine. And now you predict the next token, fine. Now, and you get the probability of that particular token, fine. Again, so let's say, okay, take a look now. So you have some probability distribution of all the tokens that are vocabulary, and you pick the top one, obviously, right? So now what you do is you flip the tokens in front of it with its own synonym. Synonym.
Okay.
Same semantically sounding words, same meanings, right? You change the tokens over here, like 1, 2, or 3, whatever. But if you have a less number of tokens, you swap with its own synonyms, and then you generate the probability distribution again over here. Fine. So if the LLM was not trained on the initial text, right? So changing the semantics of those, just the word itself, but the meaning remains the same. So in the embedding space, they'll all remain close by, right? So the output token distribution shouldn't change a lot. Make sense?
That is if it wasn't trained on that text.
Yes, if it wasn't trained on an initial guess of text, swapping the words for semantically similar words shouldn't change the next token prediction's probabilities. Make sense? But if that exact token or like exact word was used, like sentence was used, then there will be some drastic change in the probability distribution because it has kind of memorized that particular sentence, so it has overfit to the next token which has seen in the training. But in real life, that sentence may not be used that frequently. Fine. So that particular sentence was hard-coded in its memory, but once you swap the words, it kind of becomes a gender sentence again. So the probability distribution changes again to which fits a gender narrative. Fine. So again, what they do is you generate m semantically similar neighbors of x, that is, which sound very similar. And a member will obviously have a lower loss than its neighbors. That is the probability of that particular one will be extremely high compared to other semantically similar ones. So if that's not the case, you can say it was not used. But if the probability is suddenly extremely high for some particular token, but when you swap it around, it changes a lot. That means it was used. So this is called as neighbor comparison, where they swap the letters. Right? So for now, we have seen the ratio test where they train shadow models and check, and this is the neighbor ones. Second is, but the issue kind of become, at least in normal frontier models, like say Claude and all. Again, when you go back to the original discussion on privacy, where we told epsilon is the privacy guarantee, right? When you go to like extremely large models, they're not like obviously trained on, let's say, 10-15 epochs. At max, they're like 5 epochs on large data sets. So it doesn't get a lot of time to like memorize a particular data point like perfectly, or you won't have enough probability like to claim that this was trained on it. Like all of this is just probability for now. It's just reference, or with respect to this, how much is this changing. But if your dataset itself is extremely large and your model is extremely big, you are not getting enough time to like memorize something. So you can't say with some guarantee that this was used. Maybe it was just generated, by sheer luck. Unless you have very conclusive evidence, it's kind of difficult. So that's one more thing, that what they find is in a very large model, after fine tuning on some data set, it still is not extremely good enough. Right? And next is, so the latest paper in this is something called as attention membership inference attack. So for until now, what we have seen is all the attacks were based on the probability distribution at the end. Fine. What these guys did was, but the advantage of that is you need only gray box. Attacks. Gray box means you have access to the last layer probability distribution. Right? This is something called as white box attack, where you have the entire model. That means if you probe the internals, it can give you the weights, it can give you the backward propagation, it can give you the attention maps, everything. Fine. So this is called as white box attack. So this is kind of difficult to implement in the sense you won't have a lot of models to test it on. Right. Gray box is kind of easy because when people release open models, you can kind of probe into that, but getting white box models is kind of difficult. People generally don't release those models. But once they do, what these guys do is instead of just looking at the loss values, they look at how the attention map itself changes from layer to layer. Right? And what they observe is for members and non-members, that is used in training and not used in training, how the attention varies across layers is kind of consistent compared to non-members, because non-members are seeing it for the first time. So shift in attention maps, what words are being targeted, it follows a smooth pattern. So what they do is they take all these attention maps, all these values from each layer after training the model, and then they use a classifier to take the features as the attention maps, the loss values and everything, and they run a classifier on top of it to predict more like, what do you call it, member or not member. Make sense?
No, why do you use a classifier?
So you have the model, you have the attention, like you fine tune it on some data set, fine, and then for experiment purposes, and then you input your fine tuned data to get the attention map of how it progresses as you use that data set for training itself. So what they observe is the attention values, the attention map, where it's focusing on, it's much more easier to like predict compared to a non-member. A non-member, like if you put the values on a map, like on a chart, they kind of look different. Like you can separate them easily. I'll show that, I'll pause and show it. But yeah, actually I'll show it now. Yeah, so we can see from here. So these are the metrics that they extract from the model itself. Right? And the orange and blue ones show members and non-members. Right? So when you plot it, these are distinguishable for both members and non-members. So they take these values and they put it through a classifier. So that we can get, like, given a certain value, you can predict whether it's a member or not member. So they collect multiple different features. There are some 11 features, I think, and then they run a classifier on top of it to predict whether the input was member or not. Make sense? Okay. Yeah. So that is attention MI. Right. So. That's what my research is more or less about. I'll quickly wrap that up also. So in diffusion LLMs, what they have done is, right now they are still in the initial loss comparison / neighborhood type of attacks. Like given a model, they kind of calculate the loss at each denoising step, and using that loss, if it has seen it before, then the loss of each denoising step is going to be considerably less compared to a non-member. Make sense? So they use that, and then they show that it's a member or not member. Right? Now my research right now is using that attention kind of setting in this particular model, where I take the internals of the model. These are kind of what I extract from the white box model. I'll give it, like, I won't explain it right now, I'll give it 20 slides, just have a look at it. And then I run a classifier on top of it to run attention, like membership element attacks. So then for now, like, I am beating the benchmarks by some 10%. that was my research. So this was part of the course project. And one more thing which I'm doing right now is, so you saw that delta, right, in epsilon delta definition of privacy. That is given, like what's the probability that the epsilon guarantee would fail, right? So right now, what I'm working on is, how do I put it? So in each denoising step, you can like bound this delta. That is, how difficult is it to, what do you call it? How difficult is it to tell whether a data point was used in the data set trained for the model, given the loss at each denoising step. That has been only done for the continuous diffusion which you have seen, each step. I am now trying to like derive the data theoretically on math for my project. So that's the two things I'm working on. Fine? I'll just stop recording this.